Here's another very nice non-trivial example. Now, I did factor the output of y, and from the factorization scheme, I did build a sign graph. I took this b and differentiated it, factored, built a sign graph. Now this tells me where the original function changed in increase and decrease and increasing. But then I took this first derivative, differentiated a second time, factored, built a sign graph to identify when I'm concave down and concave up. Now before we put all this together to sketch a clear graph of this equation, notice how these involve cubed roots. And so I don't have any restriction of the domain of this function. The domain of this function is all real numbers. If that denominator were an even integer and the fraction is completely reduced, that means I've got more restrictions. X is strictly or greater than or equal to 0. But I don't have those restrictions. And so let's see if you and I can't put things together quite nicely. Now, just because of the sign graph, not only are these the x-coordinates of two x-intercepts, but it tells me when I live above and below the x-axis. And so if you allow me to plot the first x-intercept, then the second one, according to a sign graph, I kind of behave something like this. Something like that. I know I'm being a little sloppy because I don't see any linearity with those two terms, and so I don't think I've got line segments, but it's a start. Now, according to my first derivative function sign graph, I changed from increase and decrease about x equals 0. Oh, I've got that right. And I've changed from decrease to increase at an x value between 0 and 1. Oh, I've got that right. But notice how my sign graph for the second derivative function discussing concavity tells me that I'm concave up entirely in the right-hand plane. So in the right-hand plane, I think I've got this V shape but smoothed out. So if I could just now smooth out in the right-hand plane, maybe it behaves something like this. Now in the left-hand plane, let's see, I'm entirely below the x-axis. I'm strictly increasing in the left-hand plane, but I changed from concave down to concave up about a negative x value. Doesn't compound this. I changed from concave down to concave up about some negative x value, that one right there. But notice how I never level out because I'm strictly increasing the left-hand plane. But I don't like what I've drawn on the board because technically speaking, with the second derivative function, notice how when x is equal to 0, y prime is undefined. To me, that kind of implies the tangent line is vertical there because x is the denominator of a fraction for the first derivative function. So if you don't mind me redrawing all of this, showing that my y prime basically goes to infinity in terms of numerical value at the origin, if I can say such. Let me clean up just one last time and suggest in the right-hand plane, I changed from negative to positive with the y values. Did it again, sorry. I said change from, my goodness, I lost track of where I'm at. I said change from negative to positive with y values from 0 to 1. And beyond 1 become positive. But my tangent line is vertical at the origin, if it exists. Now, in the left-hand plane, like I had before, I may be strictly below the x-axis in the left-hand plane, strictly increasing the left-hand plane, but changing concave down to concave up in the left-hand plane, but not quite getting horizontal at that inflection point. So walking backwards, I'm concave up and then become concave down about that inflection point without actually becoming a tangent line that's horizontal or even negative. And so the inflection point occurs when x is equal to negative 1/5, whose y coordinate I'll leave to you. Just plug negative 1/5 for x here and here, and you get the corresponding y value. So I think it's a relatively clean sketch of the graph, and even if I'm sloppy, who cares? At least I've got the important details of my pretty picture.